Okay, in our last lecture we discussed a couple of different kinds of isomers. Last couple lectures we discussed a couple of different isomers. One of them was this constitutional isomer, right, where you had a molecular formula that was written as C4H, I don't know, and you can connect these atoms into different conformations to arrive at different connectivities, essentially totally different molecules that would share the same molecular formula. And we called those constitutional isomers because they differed constitutionally from one another. Then you had isomers where the difference was more or less just from the dynamics of switching between, say, the axial configuration to an equatorial configuration. So this was more about molecular dynamics, inducing changes in the conformation of a molecule, and we call these conformational isomers. And these are identical molecules in all real respects. They just differ in the way substituents are pointing, and presumably they can go back to being exactly the same if you give it enough energy or time. Now there's another type of isomerism that we need to talk about because it's an important kind of isomerism, and it's called stereoisomerism. And you can see that I have drawn, or I have stolen something from the internet here of these two molecules. And they're mirror images, and these are what we call enantiomers. All right, an enantiomeric pair are mirror images, two molecules that are mirror images of each other. And they have what's called chirality. And chirality, in the context of stereochemistry, means handedness. All right? And so you have a left and a right hand, and those two are not superimposable. Now, I cannot draw hands, but I can draw feet. So what I'll do is I'll draw some feet to sort of illustrate. And you'll notice that my feet drawings are also terrible. So aside from possibly a career as a comic book artist in the 80s, I decided to say, oh my, what is that? 1, 2, 3, 4, 5. This has 6 toes. Well, you see, I'm not a great artist in any regards whatsoever. But there you go, 2 feet, right? So if you look at these 2 feet, you'll notice they're mirror images of each other. And if you try to superimpose one foot on top of the other, try to rotate it around, do all kinds of things, you can't get one foot on top of the other. And this is something that Big Shoe has really exploited, that you have a right foot and a left foot. And you need to buy 2 different shoes to accommodate this left and right nature of your feet. And just like you cannot fit a left shoe on your right foot, well, you can. It's really the hallmark of probably being an adult that you do not confuse your left shoe and put it on your right foot. You appreciate that your left foot and your right foot are 2 different feet, and they require 2 different shoes. Just like you can imagine this molecule and this molecule are 2 different molecules, and they have 2 different, albeit modestly different kinds of properties, these 2 different enantiomers, these enantiomeric pairs. Now, how can we further illustrate it? So let's further illustrate this, all right? So let's just take let me draw on here. I'm going to draw a bond here and a bond here, all right? So this is our carbon. And then we've got a bond coming out towards you. Oop, that's got to be a wedge. It's got to be a wedge. And then this is a bond going away from you, right? So bond coming up, bond here, coming towards you and away from you. And then we're going to give these things names. So this is probably going to be a hydrogen. I don't exactly know what a gray ball is, so we'll just color it in gray as sort of a placeholder for the moment. That is obviously a chloride, And then in orange, I don't know, call it an iodine, all right? An iodide of some kind. And we'll fill these guys in over here. And put our picture there. There we go. All right. And now we've got our enantiomeric pair. They're stereoisomers because they're mirrors of each other, mirror images. And we can draw that mirror here. And what I want to emphasize here is that you cannot superimpose this one on this one. And I want to sort of show you how to think about this, and how to manipulate these things, because this is what you're going to have to do for this. Manipulate them a bit in your mind, okay? And manipulate them a bit on paper. So how do we know that this is not superimposable on this one, right? Well, we can try to manipulate it so that first, what we're going to try to do, they're going to try to flip one of these around and then set it on top of each other. So the first thing we do is we do an initial flip through, we'll call it the, what is that axis? The y-axis, right? And we do a 180-degree twist, right? So when you do a 180-degree twist, you're going to bring that iodine out and rotate it around here. And you're going to bring the gray ball and move it over here, right? And so you've got a wedge, or you got a regular dash for the hydrogen in the gray ball. So we're going to keep that. So we're going to have a hydrogen. It's going to come down to a carbon. And then this gray ball is going to also, we're not changing that. So the gray ball. So hydrogen and gray ball still have these regular dashes. They're not, I'm going to redraw them because I really want you to see. It's not the gray. That these are just regular dashes. All right, regular lines. Now the wedges and dashes for the iodine, right? So the iodine is in the back, and we do a 180-degree rotation. So the iodine now is going to be on the other side, and it's going to be in the front. So now we're going to draw something that looks like this, and we're going to put the iodine right there. And the chloride is going to go in the back. All right, so now we're going to there, and then we're going to put the chloride back here. Okay, so you can see what I've drawn here, that this does not superimpose. Like the gray ball aligns with the gray ball, and the hydrogen aligns with the hydrogen, but the iodine does not sit on top of the chloride, and the chloride, they don't match. All right, you can do another rotation, you can do another flip, try to make it work a little bit better if you want. Sometimes this is necessary to really convince yourself. And then that's a rotation about this axis. We'll call it the x-axis. All right. And so what this does now is this is going to move the gray ball. It's going to move it up, and it's going to move the hydrogen over. There's still going to be regular lines. So we're still going to have C, and we're going to have a regular line and a regular line. Except this time the gray ball is going to be on top. And this time the hydrogen is going to be back here. All right. And when you do the rotation, what this does now is it flips these two around. So now the iodine and the chloride, they switch places again. So you can see these sort of mental gymnastics that I'm making here. All right. So we do our flip. Iodine goes over. Chloride goes in the back. So now chloride is out in the front, and iodine is now in the back. All right. So what we have done in this particular case is now the iodine and the chloride are now matching up, right? But the gray ball and the hydrogen up at the top, they don't. So again, I've flipped it around, and it still doesn't match up. So there's no way to create a superimposable image of these two molecules. Now let's try this with another system, all right? So because these two there's just no way to do it, to make these things. We are now confident that these are an enantiomeric pair. All right, an enantiomeric pair, we can rest assured that's a non-superimposable mirror image. right? So non-superimposable mirror image, that implies that I can make a superimposable mirror image. And certainly if it is a superimposable mirror image, it cannot be an enantiomeric pair. It's not a stereocenter. It doesn't have stereoisomerism. So let's look at another example, all right? So we can have a carbon, right? And it can have CH3, it can have CH3. And we'll give it a wedge and a dash, all right? And these two will make different. This one will make a hydrox, and this one will make a H. All right, there we go. You know, actually, let's just make it a chloride so that we get a couple colors in there. All right, these are nonsense molecules, by the way, but we can definitely draw a mirror image, right? So if we draw the mirror image here, we see we got a chloride, and that is going to we got a carbon, and that's going to have a wedge coming out here. And then up there, CH3, and down here, CH3. All right? So that's pretty easy. Now, the question is, are they superimposable? And we can run our same sort of tests to check to see if they are, right? So our first order of rotation, we'll do the rotation around that axis, right? That axis through the molecule, as I've illustrated here. And when we do that rotation, the CH3 stays on top. This CH3 goes over to that side. So now we can draw a C here. Draw CH3 there. Oops, it's going to get out of your view. All right. And now the Cl on this side, that's going to come over here and be in the front. So we'll just draw in our wedge and our dashes here. We're going to put the Cl out in front and the OH going in the back. And you can see actually what I've drawn here, these are not superimposable either. I can, like the CH3s on the top and the left, they sit on top, but the Cls and the OHs, those don't actually sit on top of each other, which is why it's important to do this additional symmetry operation where we do a rotation about that bond, okay? And then we rotate it about here. And what that does is it flips this CH3 over to that position, and that CH3 goes back to that position. So that's going to be a rotation. So it actually, your drawing doesn't change because now the CH3 and the CH3, all right? That doesn't actually change. Well, the position of the chloride and the OH, those change because we're going to do a rotation about here and then over here, which means that those now actually change places. So we always have a dash and we always have a wedge, but in this particular configuration now the OH is in the front and the Cl is in the back. All right, and so after that symmetry operation, it's pretty obvious now that I can sit on top. Those are the same molecules, right? Those two are superimposable mirror images, these two folks. Superimposable mirror images. And because they're superimposable mirror images, those are achiral. That's actually, I like to use them. They're called achiral. All right, they don't have handedness. They're not two distinct molecules. They're not superimposable. Whereas the example above, they are. And so you'll notice really that what the difference between these two sets that I had, I drew this one up here and this one down here. If you were keenly observing, you'll note that there's actually a difference in these two molecules, and that is one of the probably obvious differences is that this has two identical groups on it, and this has 0, and none of these groups are the same. They're all 4 different, right? But the slightly less obvious difference is actually this molecule has an internal plane of symmetry. All right, so we'll put this down here. And And what do I mean by an internal plane of symmetry, actually? So if you look through the plane of the page, we can see, right, if these are stuck in the plane, and that's stuck in the plane, then you'll notice that the left and the right reflect each other. In fact, I'm sorry, the left and the right do not reflect each other. There's no symmetry in that plane. But let's take our eyeball of science, all right, and look down that side. So we're going to look at it from this side, where you've got a C and you've got a CH3 pointing this way, CH3 pointing that way, right? And then off to one side and off to the other is your OH and your Cl, all right? If you bisect this, in fact, let's just make this a little bit more obvious. Let's redraw this so it's a little bit more obvious. If you bisect this way, we draw our plane this way, we can see that there is in fact a symmetry between the top and the bottom of this molecule, right? There's a plane of symmetry here. That's a bit easier to see when you draw it in this projection right here, where you've got this sort of flat-looking configuration. It's called a Fischer projection, and we'll get more into Fischer projections in a little bit. Now, if you do the same to this, molecule, let's not use that, let's go up here. This molecule right here, oh, fine, we'll take it. We'll take the whole thing. Right? Let's look at this. It becomes a bit obvious that it doesn't really matter how we orient our eyeball of science. Well, we can orient it any way you'd like. We'll just layer down this same exact view. All right, where we still have a carbon, and now this time the old eyeball is looking at the H coming up and out at you, and the gray ball coming out at you. All right, and then the iodine going off to one side, and the chloride going off to the other. What we cannot do now is we can't draw a plane of symmetry anywhere in this molecule. The top and the bottom, they look different, and the left and the right look different. There's no real way we can draw a plane. There's no internal planes of symmetry, which means that in order for a molecule to be chiral, we can even write this down because this is an important rule. For a molecule to be chiral, it cannot have a plane of symmetry. All right, so that's just pretty good rule right there for you to follow. For a molecule to be chiral, it cannot have a plane of symmetry. All right, and even more to the point, if that's still too much effort, it's super easy to remember that in order for a carbon, at least, we can at least say a carbon, a single carbon, in order for a carbon to be chiral, you say a chiral carbon must have 4 different substituents. And 4 different substituents. All right, so that's your rule right there. And that's the only way you're going to get away from having internal symmetry in something as simple as a carbon, right? Because if you look up here, you know, there's 2 substituents are the same, and if those 2 substituents are the same, you can always draw a carbon center as having a plane of symmetry. Now, if these are two different molecules, all right, so if these are two different molecules right here, how do we go about naming them? How do we distinguish the two? And there's a method similar to IUPAC, although this one honestly is a little bit easier to figure out how to name stuff. And the naming convention for carbon, or for chirality, actually is the Kahn-Ingold-Prelog rules. Okay, and in the Kahn-Ingold-Prelog rules, essentially it's just about counting big atoms. Okay, so if you want to count big atoms and number them, that's the first step. So the first step in the Kahn-Ingold-Prelog rules is to prioritize atoms. All right. So obviously in a chiral center, you need to have something where everything is a different atom, and so there we go. That's going to be here. And we're going to have something go back here, and that will be a CH double bond CH2, and then this will be a CH2 CH3. Now this carbon has 4 different substituents, therefore it is going to be chiral. And now we need to prioritize them, right? And the prioritization is basically just looking at the heaviest atom and going from there, right? So the biggest atom is bromine, so the bromine, that's going to have the first priority. And then you look down here, and what you see is you have an ethene, and then down here you have an ethane. And the question is, how do you now prioritize something like that? Because it's not quite as obvious. Well, the ethene, we see, has a carbon attached to a hydrogen, and then it has 2 more connections to a carbon, which is a big atom than if we look down here. This carbon has 2 connections to hydrogen and 1 more connection to carbon. Essentially because this carbon right here has 3 bonds to carbon. I mean, granted, one of them is the same carbon and it's double bonded, but it does have 3 bonds to carbon, whereas this one down here has only 2 bonds to carbon. Therefore, the priority goes to this one. That becomes 2. All right. And then the follow-up, because this is very close, that has to be the 3rd priority. And then hydrogen is the smallest, and so that becomes priority number 4. All right. And once you have those prioritized, once we get the priority straight, then the second step is place the lowest priority atom in the back. All right, so now the lowest priority atom is going to have to go into the back. So we're going to use our old eyeball of science and view down this direction. And it's not super clear what I mean necessarily, but what we want to have to do is position this in our mind in a way that the hydrogen is obscured by this carbon. It's so far in the back. All right, and so that means that we're going to draw a carbon here, and then obviously the bromine is going to be on top. In fact, this is going to be a configuration where everything is just pointing towards you. And then we see that in order for this to work, substituent number 2 is going to be on this side, pointing out towards you. Substituent number 3 is going to be on this side, pointing out towards you. Okay? And so substituent 2 is CH double bond CH2, and this one is the ethane. Now there's another way to draw this, and that's sort of the opposite handedness, as though the mirror image, if we were to draw it down here, we can even draw its mirror image. And I think that instructionally is a pretty good idea to do, where you have CH2, CH, and that is connected to your carbon, and that is connected out here, and that's to your ethane. And then that goes up to your bromine, and that goes out to your hydrogen, right? And then we can draw that here. And the numbering, of course, is the same. That's still the top priority, that's still 2, that's still 3, and that's still 4. And whereas that generates that sort of projection when we look at it this one, its mirror image, we will create something that looks more like, right? Because our eyeball of science is going to be peering down here. And so that means that this CH looks like that, and that is CH to CH. And we can check to see these are now obviously mirror images also. Well, it would be if I had drawn the BR up here. Now these two are mirror images as well. So that allows us to go back and reassign our priorities. We said that's 1, that's 2, that's 3, that's 1, that's 2, that's 3. Now you draw an arrow from your, in fact that's off the scale, so let me bring that up because now it's going to become important. Now you draw your arrow from 1 to 2, from 2 to 3, and 3 back to 1. We can do that over here. 1 to 2, 2 to 3, and 3 to 1. And what that shows is that this direction over here is going to be clockwise, and this direction is counterclockwise, okay? And so because this is clockwise, we give this the label R for rectus, or upright, proper, and we give this one the label S for sinister, which is another word for left. So I'm sorry, lefties, the word left comes from the word sinister, and righties, the word rectus, upright, that's for you. So take heart though, lefties. You have a much higher chance of being president of the United States or an all-star pitcher than anybody who has a right hand, relatively speaking. That is the story of stereoisomers and how to name them.